This mouse is not only building new muscle, he's also building new brain. And you could too. Find out how running might add new cells to your brain and make you smarter.
Wide.
Join us in an experiment that rewires a brain.
Wow, this is good.
Meet a young woman whose right brain does it all. That's amazing.
Great, I hope this is on tape.
Eavesdrop on my dreams and peer into my consciousness. I'm Alda. Join me as Scientific American Frontiers explores novel ways of changing your mind.
Brought to you by
Agilent Technologies. A's, C's, G's, and T's. Hidden in all this genetic code is the genetic cause of disease. With technologies from Agilent, scientists can now start turning code into cures.
This program is also made possible by contributions to your PBS station from viewers like you. Thank you.
I've changed my mind. We say and do it every day about the gift to buy, the candidate to vote for, the route to take, the dish to order. What we mean, of course, is that we've made a different choice. We haven't actually altered the structure of our brains. In fact, the conventional wisdom is that once we're adults, certainly as we grow older, our minds, our brains remain pretty much fixed and rigid. Certainly our opinions do. Well, guess what? You're going to have to change your mind.
Hi, Michelle.
Yes.
I'm Courtney, one of the dietitians.
Hi, Courtney.
How are you?
Good, how are you?
Good. I just came over to review how the food was going to be set up for the study. Just since you'll be blindfolded, we just want
Michelle
to
Geronimo has volunteered to be the subject of an extraordinary experiment. I'm here to lend a little moral support. In a few moments, Michelle is going to lose her sight.
Is this real food?
These are food models that we use for teaching purposes.
That's a great relief. Because
To me too.
if that was the real food, I
don't know.
I wouldn't wear a blindfold if I were you. Neuropsychologist ALVARO PASCUAL-LEONE makes sure Michelle won't peek by tucking a telltale snippet of photographic film into the blindfold. Your last look, huh?
Yes. Into the darkness.
Okay, here we go.
Here we go.
It's now 9 a.m. Monday morning.
We're going to start bandaging, okay?
Yes.
Michelle will be totally blind until 3 p.m. Friday.
Okay. There are eye pockets that.
Here's the moral support I mentioned.
Come on.
Michelle, can you hear me?
Yes, I can.
Hi. To get a sense of Michelle's next few days, I'm being blindfolded for the morning.
Are you both ready to start walking with the cane?
Who's this here? Who's that, the cameraman? Yes, sir. Well, get out of the way.
Opposite the forward foot, right.
We're headed for the hospital's clinical research center.
It's a little bit
And at
long.
once, my awareness of the surroundings shifts from sight to my other senses.
Differences in the sound quality, whether it feels
Sound
more
and
open.
temperature.
Yeah.
In fact, the whole point of the experiment Michelle's about to go through is to see if this shift in sensory input has an impact on her brain, in particular on her sense of touch while she learns to read Braille. And D, it
So
feels
it's like a
thicker on the
C.
top.
It's like a C with another dot.
I'm having trouble even feeling the dots, let alone interpreting them as letters.
Eventually, you just get the shape of it, and it goes automatically into your brain as the letter, I guess.
As things turned out, my mother and I were able to leave Cuba together in 1962.
But we now need to back up a little in our story and meet Gil Bush, who's been blind from birth.
Operation Peter Pan, a program.
He earns his living as a proofreader for Braille publications. Information pours into his brain, principally through the tip of his right index finger, at an astonishing rate. For years, brain scientists have been fascinated by this skill and have wondered if it involves a change in the way the brain is organized. This little device presents Braille letters to a fingertip for just a few milliseconds.
E, I, L, O, V.
With Gil's baseline skill established, now comes the dramatic part of the experiment.
I'm just taking the magnetic stimulation coil
This coil will deliver a powerful magnetic jolt to Gil's brain, temporarily disabling the region immediately beneath it.
We're targeting the back of your brain, and in fact, the back part of your brain that we call the visual cortex.
The visual cortex handles information from the eyes, at least in those of us with sight.
Feel okay?
Feels fine.
Which makes this experiment seem rather odd. Why zap the visual cortex when what's being tested is a skill involving touch, which is processed in another part of the brain entirely?
Oh?
In fact, this is a recreation of an experiment first done by Alvaro and his colleagues several years ago.
P.
Gil's experience today perfectly replicates that experiment.
They felt very dim, like the dots weren't coming up as well as before.
Gil's accuracy declined too. The extraordinary implication is that Gil's visual cortex is involved in reading Braille, as if his brain has somehow rewired itself to recruit for touch brain cells most of us use for seeing. And this is the reason for Michelle's abrupt encounter with blindness. The question is, can her brain also rewire itself to help read Braille? In her case, after just a few days, as compared with Gil's lifetime without sight.
Or king. G.
Right.
6 butts.
But for me, 3 hours of total blindness is enough.
It is bright. Michelle,
Yes.
I can't see.
That's comforting.
Yeah.
Later, on that first day of Michelle's blindness, she goes to have her head examined in an MRI machine that will take pictures of her brain while different senses are stimulated. To understand the results, we need a brief lesson in brain anatomy. Can you show me the parts of the brain that I use when I'm looking at stuff?
Yeah. Let me open up your head.
Okay.
So basically, of course, the light would be coming in through here,
Yeah.
but it actually travels all the way to the very back of your brain. And it is this back of the brain, the occipital cortex, that is the visual cortex.
Back over here.
Back over there.
So if that's where I see, where do I feel?
Right, so information from your hand, from your right hand, will come to the left side of your brain, and specifically here to the posterior part of the central sulcus. Information from your left hand will come to the other side, on the right side of the brain.
In this day one testing of Michelle's brain, the results were no surprise. When the index finger of her left hand was stimulated, the touch sensing region on the right side of her brain lit up just as it would in you or me. But now Michelle settles down for her 100 hours of blindness. A favorite movie doesn't need the picture.
So it's like lingo for some kind of like functional
There are walks around the hospital corridors,
study.
Okay.
But I don't think they put them through the whole thing that they put.
activities to exercise your sense of touch,
Happy Valentine's Day.
and practice reading Braille. Hours and hours of practice reading Braille.
For
Until finally, it's Friday.
12:39 p.m., which means I have about 2 hours and 39, did they say 21 minutes left?
Michelle's week of total darkness was relieved by one vivid visual hallucination.
I had an image in my blindfold towards the left side, black and white still shot of a face looking towards the left. Really clear, really distinct, really odd, because it was Elvis Presley. And it's Elvis the later years, Elvis with, you know, a little more hair and the rhinestone outfit, but the white collar.
In these last few hours of blindness, Michelle returns to the MRI scanner. This time, her brain looks very different. Instead of her touch sensing region lighting up, now her visual cortex is activated. It's as if, finding itself with nothing better to do, the visual cortex has stepped in to help with a task it's more skilled at than is the touch region, making sense of symbols.
Okay, ready to start?
Yes.
This possibility is strengthened when Michelle is tested as Gil was to see if disrupting her
Different.
visual cortex impairs her ability to read Braille.
Different.
Her Braille test is a little easier than Gil's, to identify whether pairs of letters are the same or different.
Same.
Now Michelle's visual cortex gets 10 minutes under the magnetic coil.
Okay, we're all done.
Michelle, we're going to test your right index finger again.
Okay.
Ready?
Yes. Different. Different.
Sure enough, just like Gil, her accuracy drops markedly.
Different.
For Alvaro, already happy as the results emerge,
Same.
there's a bonus.
I found that my fingers have been a little less sensitive since the TMS testing, the stimulation, to the feel of the characters from the Braille task.
That's fabulous. We'll pay you another $500. No, that is actually exactly what we're looking for. We were wondering whether there would be some function related to touch that would be taken over by the visual cortex over the time that you've been blindfolded. And the fact that your fingers feel less sensitive now would suggest that that actually has been the case. Wow. This is good.
Alvaro has reason to be excited. Michelle's experience is dramatic confirmation of his hypothesis that the brain can reorganize itself in just a few days, let alone a lifetime.
I would say that the brain is like market economy. There is demand for a certain thing. We activate whatever it needs to cover that demand. There is no demand for it, then we use it for something else. It's literally like any good shopkeeper would do. You adjust whatever you offer to people passing by virtue of what they're going to need.
I feel like this blindfold has become part of my face. And, wow.
Okay, you ready? You want to keep your eyes closed at the beginning.
Jeez. Ooh. Thank you.
Sure.
Hi. When the blindfold first came off, I was a bit disoriented and a bit unbalanced. I'd been dependent upon hearing to orient myself. And then all of a sudden, when the vision came back, I was thrown off guard and had to take things in a new way now, so. But now I'm all right.
So we'll ask you to put a blindfold on again, just for the
Just
test.
for a little bit.
Just for a little
Okay.
bit of it.
Having her vision restored has in fact had an even more profound effect than Michelle realizes. When her visual cortex is zapped the next morning, her ability to read Braille is unaffected. After just a few hours of working at its usual job, her vision center has apparently found it's much too busy to any longer help out with touch.
Same.
Michelle's 5 days of blindness has provided astonishing confirmation of the malleability of the human brain.
Different.
Our next story begins in London, where, of all the brains in the world, few have been changed more than the one behind the wheel of a London taxi cab. No one can drive a traditional black cab in central London without first demonstrating the knowledge, a mental map of London's maze-like streets.
Can you take me from Winfield House, the American ambassador's residence, to Old Bond Street?
Leave by another gate, left Park Road, bear right Baker Street, full Portman Square, left into Wigmore Street, right Welbeck Street, left Henry.
Scientists recently scanned the brains of 16 volunteer London cabbies and discovered that they all possessed a larger than normal hippocampus, the area of the brain used for packaging memories before they're stored. Only months before, an even more astonishing discovery had been made about this same region of the brain.
So this is the imaging room where we...
Fred Gage, here at the Salk Institute in California, led a team that found brand new neurons in the hippocampus of Swedish cancer patients. Before they died of their disease, these patients had volunteered for a study that labeled any newborn cells in their bodies with a bright green dye. This is a slice of brain tissue from the hippocampus.
The green corresponds to the molecule that was injected into the blood of this patient 2 years before they died, which means that that neuron was born when the patient, in this case, was 62 years old. And at some later time point, it became a mature neuron in their brain.
So that was a clear indication that there were cells dividing in this mature person.
Yes, yes. So from these
This
studies,
discovery has set the field of brain science on its head, overturning the long-established dogma that once we're adults, we only lose brain cells, never gain them.
there were not only cells dividing, but cells that were becoming neurons in the adult brain.
Today, research labs all over the world are scrambling to understand the implications of this discovery. The starting point for much of this work was a study of rats done at the University of Illinois. When rats were raised in an environment that's more interesting and challenging than the usual lab cage, their brain cells made many more connections. But there had never been any hint that they also made new neurons until Fred Gage and his colleagues set up a similar study with mice. Not only did they find new neurons, once again within the hippocampus, but mice living a more interesting and active life had more new neurons than did mice sitting around being bored. The mice had running wheels as well as toys in the cage. To find out if simple exercise had anything to do with growing new brain cells, the Salk team gave some mice just a running wheel.
To our surprise, we found that the mice that were housed just with the running wheel had the same number of newborn brain cells as the enriched environment, suggesting that just physical activity or exercise alone can generate new brain cells.
Having new neurons sounds good, but do they do any good?
This is his very first time in the pool. He's never been in the pool ever before in his life.
Henriette tested her mice for their ability to find a platform hidden just beneath the surface of the milky water.
He doesn't even know there's a platform, huh?
He doesn't even know this. He knows nothing.
Has he found it?
He's found it, but basically he's being lucky. Usually it takes about 2 or 3 days for the mouse to learn this task. And 7 days of training for him to learn it really well, to reach this, for me to put him in the pool and he'll swim to it in one straight line in 2 or 3 seconds.
Henriette compared the time it took for both the exercised mice and mice housed in standard cages to find the platform.
Place it in the water.
Do they tend to go around the outside and then start to look in other pads?
Yeah.
Whoa, we found it.
It actually turned out very well for the mice on the running wheel because they managed to escape from the water faster in a shorter amount of time than the mice housed under the standard conditions. So this suggests that these mice have learned better and that they're smarter.
So running mice not only grow more new neurons, they also seem to be benefiting from all that extra brain.
Have you started running?
I've started and stopped running.
But that's, we all do that. What I can see, did you start because of this? And why did you stop?
I started because of my experimental results and because of looking at my slides with this dramatic increase in new brain cells. But it's you have to be pretty disciplined to keep it up and keep running every day.
So are you maybe hoping that further experiments will show that you don't actually have to run, that maybe just rocking in the chair is enough to do it?
What worried me is that these mice were running like 12 hours every night, and I wondered, how could we run enough to even compare to that? So we did one experiment where we brought down the time of running to 4 hours every night for 5 days, and we already found a 30% increase in cell division just after that short period of time. So I'm hoping that we can bring it down to a
something
shorter...
that we can handle.
Right.
Yeah. Good. Call me when you find out.
Okay.
The task now is to find out just how running or an enriched environment creates new neurons. Growing cells in a dish outside the brain is one way the Salk researchers are exploring this question. These are brain cells actually dividing under the microscope. The hope is to discover the chemical signals involved and then find ways to use these chemicals directly to grow new neurons, perhaps even in the brains of people such as Parkinson's or Alzheimer's patients who have lost their neurons to their disease. In the meantime, I'll never think of my own brain in quite the same way again.
There must be, in my brain right now, a lot of stuff going on. Birth and migration of cells and all. Is that, am I right about that? Should I have a new picture of my brain?
I think almost more remarkable to me than just the fact, which is remarkable enough, that there's all this movement and plasticity, that movement and plasticity and adaptation that's occurring all the time in the brain is regulated by the behavior that you emit as an individual. Our brain controls the behavior, but our behavior can also affect the structure of our brain, which in turn is going to change how we behave.
Which brings us back to those London cabbies again. Perhaps the reason for their enlarged hippocampus is that they're adding neurons with all that enrichment they're getting navigating London streets. Now just imagine how much extra brain a cabbie might grow if he ran 12 hours a night. What I didn't know while I was taking a walk one morning was that I was being set up for a demonstration that it's not just our brains that are malleable, so too are a lot of the things we store in them.
Now we're just going to witness a simple picnic scene. We want you to pay attention to how often either of the folks gets up and down. So whenever someone gets up and down, you just make a mental note of it.
Okay. I knew Dan Schachter to be a noted memory researcher, but this picnic was a surprise.
Would you like some pasta?
Yeah.
Oh, good. I love to watch people eat. Although Dan had told me to keep track of how many times the picnickers stood up, I suspected there was more to this little scene than that. But what? I wasn't to find out for another 2 days that the picnic was part of a carefully choreographed attempt to implant false memories into my brain, to make me remember as real things I'd never seen. At the time, it was like trying to keep track of a very bad play while sitting uncomfortably close to the author.
Ooh, it's cold. There's nothing on.
After 10 bewildering minutes, the picnic mercifully
Bravo.
came to an end.
Very nice. Well done.
Very nice.
Well, it could use a little more high drama here and there.
Yeah, no, but it doesn't lack for slowness. It's good.
At this point, I was politely asked to leave.
Starting with R.
The scene was played over for a stills photographer, but this time it included things that had never happened while I was there,
Ignore the sun.
which means I also missed Dan Schachter's basic premise, that memories are malleable.
One of the things that we know about memory is that it's not fixed at the original experience we have. The way we talk about the event later, the way we think about it, can affect, improve, or sometimes change our memories, and photographs are one everyday source of reviewing past experiences that may have a potent effect on memory, and we're interested in exactly what that effect is.
Great, thanks.
I want you to look at each of these for about 10-20
2 days later, I was in Dan Schachter's office at Harvard University looking at photographs.
Get cut out, is it well-centered? For each photo, I'm going to ask you for a 1 to 5 rating.
Oh, see, part of me is trying to figure out what this is really a test of. I'd have to say, you know, 4 to 4.5.
Okay,
You know, it's a nicely composed picture.
I didn't believe this rating ploy for a minute, but I graciously played along, even when I knew the photos were of things I hadn't
I
seen.
take it you don't want me to mention whether or not this was a picture of something that happened or not, because this never happened.
Right, we're not concerned with that right now. We're just concerned with your...
Showing you how smart I am.
Right.
In all, I looked at about 20 photographs. Finally, the moment I'd been anticipating.
Fishing pole.
The test. No. The question is, did I see these things at the picnic or not?
Umbrella.
No umbrella, no.
Potato chips.
No, the potato chips were in the picture. Well, I remember them in the picture, but I don't remember them on the site.
Okay, so you're going to call...
I was doing fine until...
nail file.
Yes, I think I remember her filing her nails, although the picture is also vivid in my mind, but I think I remember her filing her nails, too.
Kite.
No kite. No, there was no kite. There was a kite in the picture, but that's it.
Okay. A man's cap.
Dan was obviously trying to confuse my memory of things I'd seen for real
I think he wore a cap.
with things I'd only seen in the photographs.
Well, see, I think he was wearing a cap in the photographs. And I remember when I looked at the photograph, there's something wrong with this picture. I don't think he wore a cap,
Okay,
no.
so a bottle of water?
Yes, there was a bottle of water.
Uh-oh, this would come back to haunt me.
Folding chairs?
No.
No, no way. Pasta?
Yes. You think I could forget pasta? Come on.
It's over.
That's it?
That's it. It's out of your
So it
system.
had nothing to do with how many times they stood up.
Well, that was just to get you to pay attention to what was going on in front of you.
That's why I paid attention to everything else. Now, what I'm really interested to know is, were you able to place in my memory things that never occurred in real life?
Yes.
By using the photographs? You did?
We
You
did. Even though we told you, you knew what the game was.
Yeah.
You knew that some of the things that we were showing you in the photographs had never happened. Despite that,
This is horrible.
one was the nail file.
Yeah.
That was only in the photo.
You know, when I first saw the nail file, there was this little uncertainty. Is that real or isn't it? And then a second later, I was sure I had seen it.
In the final tally, of 8 things that appeared in the pictures only, I wrongly remembered 2 as having been at the picnic, the nail file and the bottle of water. The photographs had somehow lodged in my brain right along with my memory of the picnic itself, and I couldn't tell which was which. To understand how this can happen, we have to first understand where in the brain memory is located.
Is it possible to point to some place on the brain and say that's where memory is?
Well, there's no one place. There's no one place I can point and say, there's your memory for high school graduation, and there's your memory for having eaten breakfast yesterday. Instead of being in one place, many of us believe that the memory is kind of scattered in different parts of the brain.
The idea is that memory consists of all the bits and pieces of an experience, the sights, the sounds, the emotions, with each fragment stored in areas of the brain responsible for handling that particular sensation. So sounds are stored in the auditory cortex, sights in the visual cortex, and so on. Keeping track of what's where is our old friend the hippocampus, which functions as a sort of index for our memories. Recalling an event means reassembling all those bits and pieces. It's not like replaying a videotape. It's more like shaking a kaleidoscope. With every shake, every recall, the pieces fall together all over again. Sometimes, as in my memory of the picnic, including bits that don't quite belong.
Okay, so here's the first list.
Dan Schachter wondered if he could tell the difference between real and false memories by peering into the brain while it was remembering.
Ready, course,
12 people heard word lists like these and had to remember as many of the words as they could.
Uneven, writer.
What's sneaky about the lists is that while they're each united by a theme, they don't contain the most obvious word.
bed, rest, awake, tired, dream, wake, snooze, blanket, doze, slumber, snore, nap, peace, yawn, drowsy.
Sleep, doze, bed.
There, right off the bat, I said sleep. But sleep wasn't on the list. Again, I'd been given a false memory.
Bed.
The 12 experimental subjects all got PET scans while doing this test. Recalling both true and false memories mostly involved the same bits of brain, especially the hippocampus, the index region. But while the true memory lit up the auditory cortex, the false memory didn't. So even though the subjects reported hearing the words that weren't there, their brains appear to contain no trace of the sounds of the words.
So in a way, you really can look inside somebody's brain and tell whether they're having a true memory or a false memory under certain conditions.
Under certain conditions, within this one experimental paradigm in a group of 12 people, we were able to see some differences between true and false recognition.
Dan Schachter emphasizes there's a long way to go before this first faint trace of a false memory can be turned into a practical test that could be used, for instance, in a courtroom. Meanwhile, discovering how easily my memory can be tricked was less than enough for me.
What I think that this really brings home to me is it's very important to say not, this is what happened, but it seems to me that I remember this is what happened.
I think that's a very important lesson.
It's time for me to change my mind from the one I use most of the time during the day.
Hello.
How are you?
Now what? I sit here?
To what turns out to be a much more creative one at night.
The first thing that we're going to be doing tonight is putting electrodes on so we can measure your electrical activity and know your stages of sleep.
What's that?
It's called collodion. It's very similar to airplane glue. And what this
Airplane glue in my hair. As it turned out, only the first of several indignities that lay ahead during my night as a research subject at Harvard University's sleep laboratory.
I don't want to rush you, but I'm falling asleep.
Are you really? Good.
The study I'm joining is to find out what happens to our minds while we're dreaming.
Okay, and that's the last electrode.
Like most people, I've always been fascinated by dreams, my own especially. How do our brains come up with that stuff? Even more interesting, why? My night began with a test of the state of my brain.
This hand only. You ready? Can you see it?
The task is to spot if the second of two words flashed on the screen is a real word. Sometimes the second word seems to be related to the first. When it is, and if my brain makes the association, then I'm usually able to decide if the second word is real or fake more quickly. So by measuring my reaction time, the test can tell how good my brain is at making associations.
Bed. Bed. Ah, good.
You just climb right in.
The only association I was interested in right then was between bed and sleep. Not so easy when you know a stranger is eavesdropping on your brain.
Alan, I need you to lie quietly with your eyes closed. Okay, if you could blink 5 times, slowly.
This is
and
to
really
check the
exaggerate
electrodes near my eye. They'll be looking out for REM, R-E-M, the rapid eye movements we all make when we dream.
Great. Okay, you're all set. You can go ahead and get comfortable and have a good night's sleep.
So if you'll excuse me, I'll leave you in the care of Jen Holmes, while I try to sleep with wires pasted on my face and glued to my scalp.
Well, now he's moving, getting comfortable. And you'll typically see some kind of movement when people first start to fall asleep. He's now officially asleep. Our experiment calls for him to do the word association test several times during the night. One of them when he's asleep, but not dreaming. That's what's happening now, so I'll go wake him up. Roll him over.
No, I'm falling asleep here. I am not checking into this hotel again.
Well, after that, my night went to pieces. Every time I drifted off and started to dream, I'd think, oh, good, I have to remember this, and I'd promptly wake myself up. By 6 in the morning, Jen had been joined by her boss, Bob Stickgold, and it began to look like we weren't going to find out what my brain does when it's dreaming.
Since about 2:30 this morning, he's been having a hard time sleeping. He'll go to sleep. He'll sleep for 10 or 15 minutes here. You can hear the pens slapping around. He's rolling around in bed now. And he's been doing that for hours now.
But then, when it was almost too late, I began drifting into a dream.
If we wake him up right now, we got about an 85% chance, 90% chance of getting good REM reports. So what we want to do is wait until he gets another burst. There's some more right there. Look at these. These are really good eye movements. These are fast and they're big. So I think we should go in there now and see what we can get.
I was being propelled by the solar wind, but the wind wasn't behind me. I was going toward the sun. And then I was flying over Berlin, and I remember thinking that this was called Nightgown over Germany.
It's only about 6:30. It's still early.
Oh, it's still early. Oh.
Yeah.
Well, let's try.
Let's try. Okay. Pleasant
bye.
dreams.
With one dream in the bag, I felt better about trying for another. So that once again I could be awakened for that exciting word association test.
So how did it feel to you that you slept?
How did it feel that I slept?
Yeah.
I had a worse night of sleep at a truck route in New Zealand.
Really?
Yeah, it was an interesting...
By now, all I wanted was a little breakfast and the airplane glue out of my hair. But I was also curious, of course, about the tests I'd been taking. What did they have to do with dreaming?
That's not good.
Most dream researchers believe that during REM sleep, the normal signals to the brain from our bodies are cut off. Instead of receiving inputs from our eyes and ears, the visual and auditory centers are flooded with signals surging up from the more primitive regions of the brain. These signals, the theory goes, are completely random and meaningless.
I said to myself, because first I went
But dreams, of
out
course, seem to make
flying,
sense,
but
at least at the time.
The wonderful part about it was I went out through my nose. See? So then I had all these words I was hearing.
So the key question is, where do the stories of our dreams come from? According to Bob Stickgold, we simply make them up as we go along.
I'm a little thick this morning because I had this funny night's sleep. I still don't quite get how you arrive at the conclusion that something in the brain is supplying story and meaning and coherence to these random images, and not that they're coming up in a more coherent way already.
If you look at your dream, I mean, there you have this thought of, gee, it's going to be an out-of-body experience. And first of all, it goes out through your nose. I'm sorry. It's just hard for me to believe that someone scripted that for you to do. You were just thinking, out of body. How am I going to get out of body? Help me, somebody. How can I get out of body? And something in your brain says, oh, your nose.
So during dreaming, our brains are scrambling to make sense of nonsense. Here's where the word tests are revealing. Because subjects awakened from REM sleep are quicker at making associations between the words than when awakened from non-REM sleep, or even when they're wide awake during the day. It's as if during REM sleep, our brains are primed to put together stories from random images and feelings.
Our guesses, and it's truly just a guess at this point, is that the brain is just trying to keep up with these random inputs and trying to use everything it knows to make some kind of sense out of it.
And I think they did. It has this...
Cut into the top of a California hill is the creation of a Nobel Prize winner now well into his third scientific career. It's a place he likes to compare to older institutions with a fondness for hilltops.
Take a look around and look at this surrounding here. It's like a cloister. So when the architects asked me about the place, I said, I want it to be a scientific monastery. I don't want it to be like a church. I want it to be a place where you can contemplate and look ahead 20 years. Now in science, 10 years is about as much as you can try to look ahead. Otherwise, you're a crackpot. But we try that way.
So you have looking ahead 20?
Show a little discretion here.
Jerry Edelman has looked beyond the horizon for all his nearly 50 years in science. In 1972, he won the Nobel Prize for Medicine, having succeeded at a task that daunted most biologists at the time, figuring out the structure of the antibody molecule. He went from that to working on how living things grow and develop. And then he switched fields again to brain science. 5 years ago, he conceived of the Neurosciences Institute, a place that would take on the biggest scientific mystery of all, understanding the human mind. Which meant I was a little unprepared for my first stop at the Institute, to visit a modest and very unhuman machine roving around an indoor pen.
What is this little guy doing in here?
Well, this little guy, whom we call Darwin after a very famous biologist, and because he's based on a similar principle to that of natural selection that Darwin invented, is a creature or a device that's intended to simulate how the brain and the body work together.
How they work together?
How they work together. And the idea is something like this. It looks like a robot, but it is not a robot.
You mean it hasn't been programmed to do specific actions?
Exactly right. There is no computer program telling it, go 3 steps, turn to the right, if you see this, do that. Instead, like an animal, it's born a certain way, has a brain of a certain kind, and when it makes errors, it corrects the errors until it gets something that satisfies it.
Darwin's brain is actually much too big to be carried around in its body. The brain occupies a supercomputer in the basement and keeps in touch with its body by radio. When Darwin was born, it knew next to nothing, not even that there were 2 kinds of blocks in its world, one marked with blobs, the other with stripes. But like a newborn, it does have sight and a liking for things that taste good.
There's a gripper in front. The gripper is a little bit like your tongue. It's in a peculiar position, and it will sense electricity and conductance. So when it grabs a block, it will get a quote-unquote taste. If the taste is bad, it will drop that block, and there'll be a change in the strength of its nervous connections.
Right.
And therefore, it will learn, as it were, to stay away from a block with that shape.
In Darwin's world, it's the blobby blocks that taste bad, while blocks with stripes taste good. With just this built-in taste preference, Darwin gradually figures out what it needs to do to live the good life. The brain itself is modeled on a mammal's brain with a visual cortex to receive the camera image and a second specialized area that interprets what it sees. In the computer, simulated neurons form a network with 250,000 connections. As Darwin blunders naively around its pen, these neuronal connections begin to become organized. Here are groups of neurons firing together when it sees stripes. Entirely different groups of neurons light up for a blob. These neurons are in turn connected to motor nerves that control Darwin's behavior.
And the rule is very simple. Neurons that fire together wire together. So that when the nerve cells or neurons are strengthened after it gets a reward, that's more likely to make its behavior similar the next time.
Darwin's brain is intended as a model for our own, except that we have trillions upon trillions of possible connections instead of a mere 250,000. We become who we are through the strengthening of some of these connections between neurons that fire together and the weakening of others. To Edelman, the brain is the ultimate gooey plastic capable of near infinite possibilities, molded by its experience into one of them. Even as we watch, Darwin's experience is turning it into a creature that craves stripes and rejects blobs on sight.
Do you hit the reset button every few months and let him be born again to see
yes.
how he...
Oh, yes.
how he-
Since it's very expensive to make 20 of them,
Yeah.
we generally wipe them clean and start again. But
then you see how he learns with this new life
and
that he
each one does it differently.
Each one does it differently because its individual experience in its world is different. The blocks are in different places, and it encounters them in a different order. Each incarnation of Darwin's brain is shaped by its own particular life, just as is ours. This makes it very different from even the most sophisticated conventional computer.
If you're going hunting for birds in a swamp on a rainy day, and I gave you an Air Force computer and it was friendly and spoke English in a teacup, would you take that or would you take a dog? Okay, that's
right.
That's what we're trying to understand. How does the dog recognize novelty?
Yeah.
How do some dogs behave better than others when it comes to certain kinds of stimuli? And how does that relate to our very being as human beings, which is the key question, of course, of neurobiology, because it's at the center of human concern. Our brain and body are us.
Lately, Jerry Edelman has been turning his thoughts to a mystery so profoundly personal that it has always seemed beyond the reach of science. The unique world within our own heads we call consciousness.
We all know what consciousness is without having to ask a philosopher. It's what you lose when you fall into a deep, dreamless sleep and what you regain when you wake up. So we have a sense of it, even if we can't put it into words. And so the problem is this. How do you make it a scientific subject? How do you actually investigate such a remarkable thing, since it belongs to each individual to some extent privately?
So is this an attempt to make it a scientific investigation.
Exactly.
Consciousness
it is
itself.
Indeed. It's to find what they call, in the fancy language, the neural correlate of consciousness. What happens inside your brain when you become actually conscious of something? Well, Alan, let me introduce you to Lacey, who is the lady who really knows how to work this thing. She's going to take you inside and expose you to this remarkable miracle of modern science.
Okay. Should I take my jacket off?
Leave your jacket off.
Okay.
I thought allowing scientists to eavesdrop on my dreams was pretty brave.
Well,
But allowing a machine to peer into my consciousness? The plan here, as I understand it, is to see what happens in my brain as my consciousness switches from an awareness of one thing to an awareness of another. What looks like a giant hairdryer is actually a machine for picking up the tiny magnetic signals my brain gives off as it busies itself interpreting the world. In this experiment, my world is limited to the screen in front of me. To you, it looks like a flickering plaid of blue stripes and red stripes. But the glasses I'm wearing limit my right eye to seeing only the blue stripes and my left eye to seeing only the red stripes. My brain can't handle these two different signals at the same time, so it chooses to be aware of, to be conscious of, only one at a time. Every couple of seconds or so, it spontaneously switches. Now I'm aware only of horizontal blue stripes. Now only vertical red ones. As I record which color I'm seeing, the machine is recording which parts of my brain are responding. It turns out that neurons fire in response to both red and blue, even when I'm conscious of only one. But there are many regions of my brain where the response to a color is much stronger when I am conscious of it. It's as if the blueness, say, is always there, but springs vividly into my consciousness only when a vast network of neurons ignites together.
So think of a kind of flame playing back and forth, back and forth. The flame is the consciousness, if you will, but there's no one place where the consciousness is.
The flame flicks between regions of the brain involved in memory as well as those processing new information from the senses. Edelman and his colleague Giulio Tononi have taken snapshots of this metaphorical flame in 7 different subjects like me. At first glance, the flames look similar.
But in detail, if you look at it, all people are different.
the same thing is happening, but it's happening seven different ways because you have 7 different people.
Like
7
your
different faces, 7 different brain activity patterns when you're conscious.
7 different signatures when we sign something.
Yes.
And therefore, one of the remarkable conclusions we've come to is, I believe, non-trivial for human beings. Individuality matters.
There's an even more remarkable conclusion for non-humans. Having an idea of what consciousness is means you could, in principle, install one in an artificial brain like Darwin's.
Now, when you synthesize it, is it going to be like Alan Alda? Certainly not. It doesn't have your body. It doesn't have the same kind of structure. So it will be a consciousness. Now the question becomes, how do you check it?
Yeah, I was going to say, if you can get Darwin to...
you know how you have to check
be conscious
it, and that's
of
the hard part.
How do you get a report from Darwin?
You would have to have something like language, higher order consciousness, because otherwise you could only surmise that it was conscious.
Knowing what consciousness looks like means you could also search for it in non-human animals. Edelman has little doubt that an animal such as a dog would turn out to possess at least the glimmerings of a consciousness flame.
The difference between a dog and you, however, or as Giulio, let's say, is if you kick a dog, the next time he may bite you or run away, but he doesn't sit around plotting to remove your professorship. Okay.
We're ending our show on brain plasticity with a truly astonishing example. I'm with Jordan Grafman, looking at the brain scans of a remarkable young woman.
This is the right side of her brain. This is the left side of her brain. And what happened was, when she, in utero, she had a stroke.
Yeah.
And the stroke, not entirely, damaged a large proportion of her left hemisphere.
So that never developed?
Never developed.
What's the left hemisphere usually there for?
Verbal processing, language processing, not all aspects of language, by the way, but enough that we consider it the hemisphere that really dominates our language abilities. It also plays a fairly large role in recognizing objects, our ability to look at objects, to know what they are, and even how to use them.
So if those functions of the brain were only to be found in that area, then you'd expect that a person without that part of the brain would have difficulty saying words or recognizing objects. But this is not the case with Michelle?
This is not the case with Michelle.
Missing almost the entire left side of her brain, Michelle Mack has an obvious problem controlling the right side of her body.
He'll think, when he comes into work, he'll think straight.
But at the Catholic Church where her mother works, it's equally obvious that Michelle has few problems either with language or recognizing objects. She regularly helps out with the church records.
I take them home and I update them on my computer at home, and I bring them back to my mother and I file them.
Recently, Michelle's mother, Carol, contacted Jordan Grafman at the nearby National Institutes of Health outside Washington, D.C.
I wonder what testing Dr. Grafman will be doing.
Every month or so now, mother and daughter drive to the NIH to join Grafman and his team in a study of how Michelle's right brain copes with a workload most brains share with the left. Today, Carol told the film crew of a skill even Grafman doesn't know about.
If I say a date, you can come up with what day of the week it is?
Yeah, I think so. Yes.
Well, let me just pick it. Let me just not go too far out.
Okay.
Let's say this year, the year 2000, October 19th.
Okay, October 19th is going to be on a Thursday.
Okay, I don't have a calendar, so I can't check that. So far, you're doing great. Okay, so let me go a year later. The year 2001, August 12th.
Okay. Sunday. They're all checking.
Yeah, are you? They're both right?
They're both right.
Oh, I'm impressed.
Well, maybe we should stop at 100% correct, right? That's amazing.
Great. I hope this is on tape.
Did you know she had this ability?
Not until right now. And that's why it's fun to work with Michelle, because she's always surprising us.
Yeah.
Jordan's work with Michelle is only beginning.
All right, now draw the design as accurately as you can.
But already it's apparent not only that her right brain has taken on tasks usually done by the left, but that it's had to make some changes of its own. For instance, Michelle has problems with tests of her visual spatial skills, even though her right brain, where these are normally tackled, is intact.
It's almost a question of geography. Like there's a whole bunch of word people who have no place to live on the left side,
Yes.
and they're crowding onto the right.
That's right.
Piece of geography. And there's only a certain amount of land there.
They're not asking permission.
That's right. They're coming in. They're barging in.
Yes.
And the folks who are living there, who handle spatial stuff, are getting crowded out. Not as
Right.
many of them can do their spatial stuff. That's what it sounds like is happening.
Couldn't have said it better.
but that's fascinating, isn't it? I mean,
Yes.
there's this old saying that you hear all the time of, we only use 10% of our brains.
Yes.
It sounds like we're all using every bit we've got.
Every bit we've got, and we're trying to stake more out if we could.
Right, and it's almost as if there are parts of our brains competing for
Exactly.
for a place to work.
Exactly. As you learn new things, there's always somewhat of a cost. There's a finite amount of space and a finite amount of tissue, and you can enrich that tissue, but you're also going to compete with adjacent territory as you learn new skills and have new abilities. And you use the whole brain, and the whole brain is a competitive organ. Each piece of that brain is competing with its neighbors to get more territory, to have more action, and it's happening now in you, and it's happening in Michelle as she takes the tests and develops throughout her life.
As we said at the beginning of our show, we're all having to change our minds about our brains. Come visit us at PBS Online. Scientific American Frontiers can be found on the World Wide Web at pbs.org or America Online, keyword PBS. Some people can hold their breath like that for almost 8 minutes. And they think it's fun, too. On the next edition of Scientific American Frontiers, the people who push themselves to the limit. I'm Alan Alda. Join me next time to meet the super people.
Brought to you by Agilent Technologies. The next generation of wireless communication is here, and technologies from Agilent are helping make it all possible. We've taken the fiction out of science fiction. This program is also made possible by contributions to your PBS station from viewers like you. Thank you. To order this episode on video cassette or other programs from Scientific American Frontiers, call PBS Home Video at 1-800-PLAY-PBS.
This is PBS.